Hello, everyone. Welcome to the second video in this series. This, again, is optics. We're talking about convex lenses, convex mirrors. So, again, we suggest that you review the intro video on the concave and convex mirror terminology and sign convention. We did a video already on how we do ray tracing and apply the thin lens equation for a convex mirror. And in this video, we're going to do exercises, and also on the next video as well, we'll do more exercises. So please let us know what you think about this stuff, and let's begin. So here we have a 2 centimeter tall object placed 45 centimeters left of a convex mirror of this much focal length. So H sub O, let's go to white here, is 2 centimeters. The object is 45 centimeters. And the focal length, although here it says 18 centimeters, in reality, it's negative 18 centimeters. That's when it enters into the equation. It has to enter as a negative because it's a convex mirror. Let's describe the image. So first, we do need to get the distance to the image. So 1 over di plus 1 over do is 1 over f. So again, do it one time. Bring do over. Combine the 2 on the right into do times f, do minus f, and then flip. And now we plug numbers in. So di, and we expect it to be negative. Okay, do is 45, f is 18, over f is negative 18. And then here we have 45 minus negative 18. Okay? So let's see if we can simplify things out. So this is again the negative 45 times 18, negative 60 plus 63. So we are going to get our negative out. Okay. I could not see anything. Yeah, maybe divide by 9. This will give me a 7. This will give me a 5. That's about it. Okay. Cannot simplify anymore. So now 5 times 18 divide by 7. It's going to give me roughly 12.9 centimeters. Okay. So the image is negative. The I is negative, which is good. Okay. 12.9 centimeter is closer to the image, to the lens, than the object. That is also good. So let's look whenever we get to the ray tracing, we'll see if we can get the same thing. So now magnification. Magnification is negative di over do, which is also hi over ho. Let's get the magnification first. M negative, maybe I want to put it, let me see, do, yeah, we could put it like this, just negative, roughly 12.9 over 45. Okay. So that is Let's see how much that is. 0.28. Negatives cancel. It's actually roughly 0.29, we can say. Okay. So let's see the height. And since this is positive, well, we have a virtual image. And we know that from a convex mirror, all the images are virtual, no matter where the object is. The object could be close to the lens, could be far away from the lens. The image is going to be virtual all the time. Now, h sub I over h sub O equals m. So h sub I equals m times h sub O. So that would be 0.29 times 2. So roughly 0.3 times 2. Okay, so roughly 0.6. So that's going to be 0.58 centimeters. Well, let's see if ray tracing corroborates this. So here's the 2 centimeter object. Here's the focal point. Each is 9 units. So here's each square is 9 units. So here's the ray that's parallel, appears as if it's reflected coming from the focal length. Bam, goes out like that. Perpendicular to the mirror, reflects on itself. Perpendicular to the mirror, meaning going through the center. It actually doesn't go through the center, right? It just bounces back on itself. And through the focal point, it's as if it's going through the focal point, gets interrupted by the mirror, bounces back parallel, and then trace it back, and they all meet over here somewhere. Okay? So let's see. The object is roughly, well, from right here, it's about a half, maybe 60%. And it's, if each unit is 9, so that's 9, and halfway between 9 and 18, yeah, 13, 14, something, maybe around 13, right there. And 9 plus 4, 4.5, roughly 13. So what did we get for roughly 13? Good. That was a very good drawing, I may say. Very close to where we want to be. Okay? Let's look at another problem. Convex mirror with a focal length of 20 centimeters. So automatically F is negative 20 centimeters. Because it's a convex mirror. Forms an image at 10 centimeters away from it. So D sub I is also negative 10 centimeters. Recall that the focal length, the radius, and all the images produced by a convex mirror are all on the dark side. So they're all negative, okay? What is the object's location? In other words, what is DO? And what is the magnification? So let's compute DO. So again, 1 over DO plus 1 over DI is 1 over F. Bring DI over. And now that's what we're going to get. Again, we did this in both lenses in the cockney mirror. It's the same type of equations. We're going to get something like this. Okay. And now we plug numbers in. We expect DO to be positive and farther away from the lens than the object, than the image. So DO, DI is negative 10. F is negative 20 over DI is negative 10 minus 20. So this is plus at the top. So that will be 10 times 20. And you have negative 10 minus 20. That's plus 20. Let me put it in. So we get a 10 in the denominator. Well, this 10 cancels this, leaves me with 20 centimeters. So it's positive, further away from the lens than the object, than the image. So this looks like we're on the right track. Okay. Magnification is, let's put on the third column right here, is negative DI over DO. So here's the negative. DI is negative 10. DO is 20. Negatives cancel. That leaves me with 1/2. And positive means we have virtual image. And of course, it's going to be upright. All right, well, let's see. So now I'm going to start with a DO of 20, an F of 20 on the other side, and see if the image lands at 10. So here's 20. Again, every unit is 4. 1, 2, 3, 4. Is 5. So first ray, parallel to the axis, reflects as if it's coming from the focal point. There it is. The second ray, perpendicular to the mirror, reflects on itself. Again, perpendicular to the mirror, meaning if it continued, it will go through the radius, just like this. But then the mirror interrupts it, bounces it back on itself through the focal point, never makes it there, gets interrupted by the mirror. Okay. The reason I'm drawing this dashed line is to show you that this ray actually goes through the focal point, then bounces back parallel, and they all trace back. All the reflected rays trace back over here, and there it is. So it is at 2 units, which is 10 centimeters. It is half at 1. The height is 1. Here's 2. So the magnification was a half, which is correct. Okay. So this is very good. It matched our computations exactly. And I think this is it for this video. In the next video, we'll do more exercises. Hopefully, we'll see you there. Please, again, drop us a note. Tell us what you think. Like, share, subscribe, and spread the word on your social media. Again, thanks for your time. Bye.